participant. So next we have Chandrika Dutt, research leader at Avasant, who co-authored the report by NASSCOM and Avasant of quantum future in India. So I kindly welcome Chandrika Dutt to give her insights and give her ideas on quantum computing and what is the future of quantum computing.
Great, sounds good. Thank you so much for inviting me today, and I just hope you find basically some areas which are new and you've not heard anywhere in any webinar or any conversation. So I really hope there are some new takeaways from this conversation today. So I did share a PPT. Maybe we can just take that up later.
But yeah, sure. Okay. Should I present the PPT?
Yeah, I'll let you know, but I just want to start this talk by basically, understanding. I understand that everybody is well versed with quantum. At least they know what quantum is, how different it is from classical computing. So, we're all at that level. Now, once we've established that, I would just like to say that you all must have been tracking this space, and given the ongoing initiatives in quantum, we have established the fact that quantum computing has the potential to revolutionize science and engineering. But I would like you to take a step back to understand how it all actually started. So interestingly, a couple of months ago, I had this opportunity to speak with the director at IBM Quantum Sales at one of my company events. And he said that back in 2016, there were a handful of people at IBM who had put up a 5-qubit quantum system online, just casually thinking that there must be someone out there who's willing to try it. And to their surprise, thousands of people, they signed up for it. And that's when they actually thought of making it a commercial business. So selling quantum computers for commercial benefits and making it more accessible to people. By the end of 2017, they actually started engaging in these discussions with clients for quantum applications. And today, as we all know, IBM offers somewhat around, I think, 1820 quantum operating systems, which range from 5 qubits to up to 127 qubits. I think that's the latest that they've got. Most of them are freely accessible for research and development. But if you want to use the systems for commercial applications, you can access it. I think there's a price around 1.6, 1.5 per runtime second USD that they charge. And they also have published a roadmap to help people plan for quantum. So if you guys haven't taken a look at it, please go ahead and do that. And I think a couple of weeks ago, they also shared a more updated roadmap with error corrections that they are doing. Now, you must be curious why I'm telling you this story. It is actually because a few weeks ago, NIST announced potential candidates for PQC. And that kind of set an atmosphere of euphoria as everybody thought we are closer to the realization of commercial applications of quantum, specifically in cybersecurity. In fact, many tech companies, they also started building solutions around it. So just to take an example, there's this company, Vicekey. So they are a cybersecurity company, and they are implementing post-quantum algorithms to secure semiconductors by exploring NIST's PQC candidates that they just recently announced. They are actually also working on defining the recommended practices for performing these trusted network layer onboarding, specifically for IoT devices with NIST. But what happened a couple of weeks later on, a bunch of scientists, they reported that they were able to crack an algorithm psych. I'm not sure of the full form. You can check that up. But there's this algorithm psych that is still actually under consideration as part of NIST's PQC program. And these set of scientists, they cracked it using a mathematical approach in barely 1 hour. Now, this is perhaps a bit concerning that this is the second example in the past 6 months of a scheme where that made it to the third round of NIST review process, but then it got broken using a classical algorithm. And just very recently, I think a day or two ago, there's a leading mathematician. He announced that he's launching a legal action against NIST for lack of transparency in post-quantum selection process. Now, my entire point here is I don't want you to feel bogged down if the trajectory of quantum development is not moving fast enough, or maybe per the industry expectations. I mean, you guys taking up this certification course is pretty much a validation of the efforts you're willing to put in quantum development and enablement. But, as they say, great things do take time. Can we have the slides, please? And also, I really encourage, people, whoever they want to turn their videos on. It's a bright, beautiful morning. Let's have some show of faces. Yeah, the next slide, please. Right. So, nevertheless, I believe that the first set of commercial applications, they will evolve in cybersecurity and sensing. So you can go through the list of use cases that are mentioned here. They're basically defined in two eras. So one is the NISC era, which is up till 2027. This is what Avasant projects. And post that, once we have fault tolerant quantum computers, we are looking at more advanced applications. Sorry, I think somebody is joining in. Yeah. So we are looking at more advanced applications such as protein folding, quantum internet, space exploration, all of that. But nevertheless, I believe that the first set of commercial applications, they will particularly involve in cybersecurity and sensing. Why I say this is because these areas are more mature. And in terms of cybersecurity, I would say it's not optional. It's more of a mandatory or a necessary situation where everybody needs to protect the current data from future cyber attacks. Now, all data doesn't need to be protected. All the relevant sensitive data, that data needs to be protected now. Speaking of quantum sensing, I feel more sophisticated solutions are on the horizon. And just to give you a broader sense of what's happening in the industry, there's particularly this company, Qcontrol. They are an Australian startup. They specialize in control engineering solutions. So this company has actually created a quantum sensing division, and they're developing a new generation of ultra sensitive quantum sensors, which will be used primarily in, say, measuring gravity, motion, magnetic fields. But the exciting part is that their unique focus on critical challenge of stabilizing the hardware when placed on a moving object or a platform, or within complex environments which are subject to a lot of noise. To be honest, such devices can have real world impact in defense, specifically positioning, navigation, timing, and also more enterprise specific use cases such as minerals exploration, weather forecasting, space exploration, and stuff like that. In fact, many applications that you see in the beyond 2027 era, they are being explored now. For instance, there's this leading chemical company, BASF. They are exploring the use of quantum computers for weather prediction with a vendor called Pascal. Now, while all this is true and nice, and I'm sure you must have heard about it, in most of these webinars and talks, there are two specific use cases of quantum computing that really stand out more than others for me. The first is quantum computing having a future as a sustainable technology. Now just think about it. we need quantum computers for complex processing. But sure, we do need to tackle the rising energy concerns with classical computers too. There are a set of researchers in the University of Massachusetts, and they reviewed a prominent architecture of natural language processing. And what they found was the model at one point of time, it required, I am forgetting the number of kilowatt energy that it required, but for I think approximately 100 or 150 hours it required that particular amount of energy, which actually translates into, if you just calculate that, it generated the same estimated carbon dioxide emissions impact as say 50 or 60 humans in their entire life cycle. So that's a big number that we're looking at. And other than that, there are various other vendors who have showed such concerns. Just to take an example of IBM, they have actually reported that next generation machines, they're going to take up to 50, 60 megawatt of power just to run. And it is quantum-based calculations that can really help with these energy concerns. So another important use case that nobody really talks about, if we can move to the other slide, please. Great, thanks. So, like I said, this is a very innovative use case, and it really talks about the role quantum will play in enabling the ecosystem for metaverse. Now you look towards your right-hand side, I've highlighted quantum and supercomputing for you specifically over here. There is a huge gamut of technologies mentioned here, which will be enabling this metaverse ecosystem, but quantum specifically plays a very crucial role. Sorry, was that a question? Okay, I'll just go on then. So, and I'm sure, like, all of you must have heard of the term metaverse. It's a hard miss these days, as every second company is jumping on this bandwagon. But just for clarification, those who don't know, metaverse is essentially a digital ecosystem that builds a virtual world that more or less mirrors our own, right? And it has the same set of features our world has, such as avatars representing us and what we own, digital real estate, gaming, media, retail, commerce. It's everything under the sun that you can think of. However, there's a catch. We at Avasant, we believe that there is not just one metaverse. There is not just one virtual world, one augmented world. There will be many metaverses. There will be entertainment-oriented metaverse. There will be a metaverse for gaming, for social-based metaverses. There will be metaverses for business collaboration, and even metaverses, specifically for, say, healthcare providers, educational institutes, and maybe, one day we would be having a conversation on metaverse. Who knows? Therefore, we prefer the collective term called the omniverse. Omniverse is nothing but basically an assemblage of, say, many verses, which are either owned by companies, governments, and other institutions. Now, this metaverse, it requires significant computing power to stream entertainment, to render the digital world, and also to track data, because there's going to be a massive flow of data within these exchange of data within these metaverses. And it is only and only quantum computers that have the potential to not only do that quicker, but also to do it cost effectively and with less environmental impact. Now, moving on to the next slide. This is basically a study that we ran with NASSCOM very recently, and this is available in public domain, free of cost. You can visit Avasant website or NASSCOM's to download this report. So don't get bogged down by these tags here, transformers, accelerators. just to cut the long story short, you would find specifically quantum computing making an impact across these categories. So how these categories were defined, there was a 14-point scale model based on which we defined, which set of companies are transformers, accelerators, beginners, but that's not relevant here at the moment. What I'm trying to say here is quantum is of interest across companies, across these categories, right? And I would say in the past couple of months, a lot of quantum applications have surfaced. But I personally feel that having a quantum roadmap is the most important thing here. While all these enterprises have shown interest in running a POC in quantum or maybe setting up teams, but I feel understanding the company's business problem, their business problems, performing an opportunity assessment, analyzing the readiness of their IT infrastructure to actually be able to adopt quantum, and also most importantly, identifying use cases that best serve the organization. Now, I would like to just go back to a question that was being asked when I just joined in, whether payroll processing is a relevant use case for quantum or not. So just take an example of a company who's selling pizzas, say Domino's, Pizza Hut. It would sound silly to you, companies like these adopting quantum to sell pizzas. You would be like, there is no business case. But yes, there could be a business case. If there are SLAs involved, for instance, if a pizza doesn't reach the customer, say in half an hour, the pizza is for free. I think Domino's did that years back. So if there are SLAs, such SLAs involved, and if a company can save, say millions of, dollars adopting quantum, say even for a basic application, as I mentioned, selling pizza, then yes, it makes business sense for that particular company. So just to answer that question, payroll processing, it entirely boils down to the kind of ROI you can generate on that use case. If it can help you save a lot of money, companies should go for it. Another interesting example I would like to take is of Volkswagen. So they were early adopters of quantum, and they have been working on several use cases across the manufacturing value chain, be it a paint job optimization, route optimization. These are good problems to solve, but it doesn't mean all manufacturers need to start here. They need to ask themselves, what are the applications they care for, and to do some introspection and analysis to understand what are the critical problems they want to solve with respect to their business. It could be production flows, it could be robotic scheduling for complex products such as automobiles that are actually very complex, and their simulation and optimization is very compute intensive. Or it could be a simple supply chain using near-time decision-making based on changing market demands. So identifying use case, in short, is the first step. The second step is enterprises across industries have to be actually very realistic with their quantum agenda. I just mentioned a use case, an incident with NIST. So we really don't know when quantum computers are going to be there, right? We are not going to solve complex issues around climate change, world hunger, or break the RSA key in immediate future. But definitely the journey has to start now, because the cost of doing nothing, it could be a lot more, right? And also, if you take a holistic view at it, a lot can be done with the existing number of qubits and the abilities of more mature and advanced solutions like QKD, QRNG. So taking a note of that is also very important. Further, I feel executive buy-in is very, very important, and this aspect is sometimes neglected in enterprises. Because an enterprise may get through a quantum POC, but they would need executive sponsorship for the implementation, the final implementation in the business architecture. In some organizations, it is a top-down approach where senior management understands the strategic role of quantum and they set up teams to identify use cases, run POC. But in most organizations that I've seen, it's usually a bottom-up approach. And these technical experts, they could be PhDs, they could be coders, they actually find it very difficult to explain quantum to top management. The moment they start speaking of, say superposition, coherence, it may perplex the management. Instead, it's important the teams start small. They analyze the results delivered by quantum and the limits of the technology. They should not tackle a complex problem in the first go. So going back to my point around having it explained in a clear manner to the management, how one in an enterprise can communicate the business value of quantum to senior executives is maybe through consulting companies, where they come into the picture and they handhold the organization in the quantum journey. Because the way I see it, CTOs, they may have other digital priorities that are looming large for them. So it's difficult for them to justify the ROI on quantum in the current scenario. But there is absolutely no perfect way to go about it. Sometimes because, the goal is not just to solve the problem, but to build a competency to be able to do it by themselves the next time. Such enterprises may want to outsource certain applications, but still they would want to know how to build or how to run applications on quantum, right? In some enterprises, there is a dedicated team, say 8, 10, 12 people who are managing big quantum programs for the organization. And there are some successful organizations that want to build a broad support structure across the organization where other business units are also identifying the use cases and the potential of quantum in their domain. A very good example here is AXA. It's a European insurance provider where they are slowly and very systematically building support for hundreds of people in the organization on identifying the potential of quantum. They are building organizational support in a very, very broad sense, and they're educating and training the people. They find that a key element. But I personally feel as quantum becomes more strategic in nature, enterprises will want to protect their IP. So the question becomes who owns it, who writes it, and who can improve it over the time. Many leading organizations who feel quantum is going to be critical for their business operations, say Volkswagen, JP Morgan, they may want to own the IP, which is generated from the research work they are involved in at the moment, so that they don't have to license it or, they just don't have to license it from the market later. But the best way to navigate from all these, circumstances and situations that I've mentioned, it depends a lot on the risk appetite, the digital priorities, the budgets and ambitions of the organizations. Right. Moving on to the next slide, I think. So this is from another study that was earlier referring to. This is a study that we did with NASSCOM early this year. It was to identify the impact of quantum on India's economy. What are going to be the relevant use cases? This number here, if you see 280 to 310 US billion dollars, this is the impact that we identified for quantum on India's GDP by 2030. And some of the industries that really stood out in the Indian scenario are banking, high-tech, manufacturing, and defense. And I'm going to take that up, one by one. So there are 4 factors that were considered in arriving at these industry-specific figures. And again, this report is available freely on NASSCOM and Avasant's website, so feel free to grab a copy post this session. So these four factors, they basically are, we considered the breadth of the quantum use cases in a particular industry, the kind of impact it would have on India's GDP, what is the maturity for quantum adoption in that industry, and are there any early signs of use case development? So for instance, we do see that in banking in India. But let's just touch base upon manufacturing first. So quantum computing adoption, it will be accelerated in use cases like I just mentioned, paint job optimization. Then there are some interesting companies, doing carbon capture with quantum. They are discovering a new catalyst for carbon capture. Then optimization and routing of warehouse robots in supply chain. And globally, if you see, there are a lot of auto companies, Daimler, Hyundai, Toyota, and the list just absolutely, it just goes on. They're leveraging quantum computers to discover more sustainable batteries for electric vehicles. The kind of features they're looking for is faster charging capability. There should be higher energy density and less flammability. I mean, that's the last thing we need in EVs, catching fire, which is unfortunately very predominant nowadays. Switching gears to banking and finance, there are some more advanced use cases being explored at a global level, which is portfolio optimization, asset trading. But if you look at it from Indian banks' perspective, there are bigger problems to solve. There are unique problems to solve. So I think the first set of use cases for banks in India are going to be collateral optimization, NPA optimization. So I think a lot of geo-specific nuances will definitely arise. In defense use cases, I think they're primarily going to be around security. Using quantum to secure sensitive military conversations, secure government data, establish long-distance satellite-based communication, quantum communication. This is something ISRO is already working on. In sensing too, there is a deep interest by Indian government. Just to name, Indian Navy is actually doing well in this area. They are investing in quantum sensors to detect and track motion in the absence of GPS in deep underwater or very high up in space. I think this is pretty much, but I would like to wrap up this conversation with what's next on the horizon for quantum computing. So first of all, I see that government sector will continue to be the biggest consumer of this technology. And this will actually increase the faith, the confidence in enterprises and industry as a whole in the future of this tech. There are actually many new and crucial initiatives happening on this front. So just to pick, a couple of examples, very recently, Rigetti was awarded a contract by a Defense Advanced Research Projects Agency. I think approximately it was for $3 million spread over 3-4 years. And the idea is to develop benchmarks for quantum application performance on large scale quantum computers. Recently there was an incident in China where a lot of sensitive information was leaked, and the Railways Department, Railways Academy in China, they are also planning to bring up a quantum communication to high-speed rail. But I think one particular initiative that really stood out in this entire year so far is US announcing a bipartisan bill that will require all federal government agencies to beef up their defenses against the potential attacks of quantum computers. Now, this is primarily focused on prioritizing the migration of federal agencies' IT infrastructure to PQC. But the good news is if this legislation is passed, it may have something you can call a ripple effect. So as the government insists on PQC methods and measures, there are other vendors and enterprises that would follow the suit. Another thing that I feel is going to be very relevant is going to be full stack quantum computing. Now, as I just discussed that IBM was one of the first companies to make a full stack commercial quantum computer, and then later came in companies like Google and all. But as quantum actually continues to prove its practicality in commercial applications, more technology companies are going to jump on this full stack quantum computing trend. Now, this could be either by building it in-house or by acquiring or partnering with a company to cover the entire value chain. Now, why is it essential to build a full stack ecosystem? There are many reasons, but just to highlight a few. So building the quantum computer stack, building the crucial layers in the quantum computing stack, in-house, it will definitely avoid any disruptions that could be caused by partner dependencies as components across the quantum value chain, say hardware, software, or maybe allied tech like control solutions, they're maturing at a very uneven pace, right? So hence, it's just important to have all of that in-house. So, once you have, say, in case of a hardware company, once you have a full scalable quantum computer ready, you really don't have to be bothered by what's happening in software or, the allied tech. Secondly, a one-stop shop will definitely help capture a bigger pie of the market opportunity, as a comprehensive orchestration platform will definitely ensure client stickiness. And there is a possibility to actually engage in contracts with high value, because I'm not sure if you've noticed, but quantum companies, they're burning cash exponentially. So big ticket contracts can actually, give them some cushion against the widening losses. Then another trend that I can think of, and it's very relevant, I'm not sure if you've heard of it yet, but there's something called distributed quantum computing. Now, this is important to scale distributed gate model quantum computations because this is going to be very crucial. Now, before that, it's important to understand for all of you that a quantum computer can be built on different architectures. Now, these architectures could be ion trap, superconducting, and all of them, they have their own trade-offs, right? So for instance, ion trap based qubits, they are slower, but they are actually more accurate technology when you compare them with superconducting. So this makes them more relevant for use cases such as, say, drug discovery. And superconducting qubits, they could be more relevant where, time and speed is of essence, say, trading. So distributed quantum computing will actually help bring the best of all these architecture types on the same network. Then there's something like blind quantum computing, which provides secure access to quantum computers in the cloud. Now, this is something to look forward to in this space because what if you're not comfortable, somebody's not very comfortable sharing a particular information with a quantum computer? I mean, say in terms of healthcare use case, maybe I'm not comfortable sharing my DNA details. So blind quantum computing overcomes that challenge of sharing sensitive information on quantum computing. This is actually going to be enabled by quantum networks, which a lot of consortiums, specifically in Europe, if I have to say, they're working on it at the moment. But for any of this to happen, we first have to tackle the challenge associated with error rates. Now, if researchers can reach, say, 1,000 qubits with small error rates than today, then I think it could be a real inflection point. The immediate goal is to get a 1000 qubit machine to an error rate of 0.01%. Now that would make roughly one error in every 10,000 operations. There are a whole challenges that need to be solved to get there. But if we can actually build a chip with 1000 really high quality qubits, then it becomes believable that we could build a much larger chip with millions of qubits. Now, as per the timelines shared by IBM, they can deliver, I think, 1000 qubits with real low error rates by 2023. But nobody really knows. I mean, it could happen a bit earlier. The reason I say this is because a lot of companies are coming out of stealth with their innovations. It's actually getting very hard to keep pace with the technological advancements in quantum. I mean, every day there is a new breakthrough. So this is pretty much what I wanted to talk about today. I'm open to taking up a few questions, if any. And do let me know, if there's a particular aspect in this conversation that you did not understand. Happy to, share more inputs and insights.
Ma'am. Hello.
Yeah, I can hear you.
Ma'am, can you explain the metaverse slide again? I wasn't able to understand the diagram.
Okay. So here, if you look at the aspects of verse, I'm talking about the left-hand side. And by the way, this rubric is also available on Avasant's website. And we have a paper on it. Let me just quickly see if I can share it with you, the link of the paper. Here. Here's the link. You can go ahead and download it. So all these references that I'm giving, they're all freely available on our website. So moving back to this this diagram. So how to look at it? On the right-hand side, these are digital prerequisites for enabling Omniverse. As I mentioned, Omniverse, you must have heard of Metaverse. So Omniverse is just basically if you combine all those verses together, metaverses together, you get Omniverse, because there's not going to be a single metaverse, as I mentioned earlier in my conversation today. So digital currencies, quantum computing, advanced networks, biometric technology, all of them are going to be digital prerequisites in building this metaverse ecosystem. But all of which I feel quantum is going to be the most crucial aspect, because you need to process data at a faster speed, right? Now, moving at the left-hand side of the diagram, these are the aspects of a verse. So what can you actually do in a verse? You can have digital real estate. Just to give an example, I think there's this singer. A lot of singers are purchasing land on Metaverse. Daler Mehndi bought a land actually on Metaverse. He calls it Balle Balle. So you could buy a piece of real estate on Metaverse, you could sell products, you could do a lot of retail, commerce. A lot of banks are also on Metaverse these days. So JP Morgan was the first bank to actually launch the banking lounge on Metaverse. Later came in, I think, HSBC, and I think in India also, I think Union Bank became the first bank in India to launch a banking platform, a banking lounge on Metaverse. So I hope this helps you understand a bit about this.
Yeah, thank you, ma'am.
Thank you for it's really wonderful talk covering the entire landscape of quantum computing. Can you speak more on startup landscape, because most of your talk was focused on established companies and how they're getting towards adopting quantum computing.
Right. So specifically, do you want to know about the startup network in India or at a global level?
Global and India, both would make a lot of sense.
Okay, sure. So basically, we see a lot of quantum trend, as you just, startup trend in quantum, as you just mentioned. A lot of these startups, they're churning out of universities, right? So very recently, there's this company, if I have the name right, Camp Graphic. So this is a startup that spun out of Cambridge University. And what they're specializing in is graphene-based photonics technology. Then there's another startup that goes by the name Atlantic Quantum Emerges. They spun out of MIT's Engineering Quantum Systems Lab, and they're going to develop superconducting quantum computers with really high quality qubits that are needed to solve these hardest computational challenges. So my point here is most of these startups, they are coming out of research institutions and educational institutions. In India, there's one particular startup that is making a lot of noise in the industry. It's a cybersecurity. Let me just quickly check. QNU Labs, sorry, yeah, QNU Labs. So QNU Labs is one of the most oldest and you could say, a company with more mature set of applications in cybersecurity. They even bid for a European contract, which was, I think, worth 500 millions or something for developing a quantum internet in Europe. So it was one of the bidders among very few competing against ID Quantique, Quintessence Labs, which is based out of Australia. So there are few startups in India that are making a lot of noise. But then there are just few. Most startups you would find in Canada, you would find in Europe, specifically Germany, UK. So because it's just easy to nurture startups in those locations. In India, there's a lot of bureaucracy. It's just not an easy market for a startup to come up and survive. Government support is also very limited. There's a lot of explanation that is required as to how a budget is going to be used and stuff like that in India. It's easy to source funding is what I'm trying to say in countries outside India. So hence you would see a lot of startups flourishing abroad.
Thanks a lot.
Hi.
So, yeah.
One question. In your opinion, for a medium-sized company that has many problems to solve, I want to explore a solution with a quantum computing proof of concept. How many people should form a research team, and how much time to spend to obtain a valid use case?
Well, I'm not sure of the specifics that how big a team is going to be, and especially in Europe. It just depends on the kind of problem, the use case that you have. Some are tougher than the others. Some are even easier to do, right? Given the number of qubits we have in hand. So it just depends on the size, as Monica also, I think earlier she mentioned to you, it depends on the size of the scale, the size and scale of the organization. It depends on the complexity of the use case that you're trying to solve. And that's how you form a team around it.
Compliment. If you suggest wait 2 years or 5 years when the technology is more evolution. My example is for usual company, for example, utilities, energy, distribution, generation. This for this is my question.
For exploration of, so if I hear it right, your question is for exploration for mining. When will quantum become more relevant?
Exploration con proof of concept, investigation, no? How explain?
Right. So these POCs are happening. So to be honest, POCs are happening across board. for mining, exploration, or in any particular industry that you pick. So POCs are happening. So what it would really require in such a in such a POC project would be there would be a consulting company, right? As I mentioned, consulting companies are required to handhold the organization in this entire quantum journey. And then there's going to be a vendor, basically a platform provider, depending on the problem that you have. So he would be selling that product. Then there's going to be service providers in the play, right? Because these are the guys who are going to do implementation. And just to highlight it, because I did this study last year and I interviewed a couple of folks in India. So at that point of time, Indian service providers, they just had certain use cases, but there was not a formal plan of action. Now this year, if I look at it, Tech Mahindra has already established they have established a metaverse lab, and they've also established a quantum computing university, right? So all of those developments are happening. Service providers are also maturing the way the product is maturing in terms of how it could be implemented, because this is a new ball game altogether for all stakeholders, for all participants. So I think these are the three main participants in any POC project or any final stages implementation.
Okay. Okay.
I have a very trivial question.
Yeah. So there's no trivial question in quantum. Please go ahead. Everybody's learning everything.
So it said like few qubit, like 50 qubit processor can achieve in few minutes or a day what a supercomputer would achieve in 10,000, right? And that could be because of some architectural difference. What is that actually, if you have to explain in, to a layman? And second part of the question is, when we are using quantum computer, there are, till now we achieved a lot of efficiency through algorithmic optimization. Is there anything which changes in terms of algorithm, or can we use the same traditional algorithm on the quantum computing also? Is there any modifications? 2 bits.
Right. So to answer your first question, are you aware of the fundamentals of physics? How basically a quantum computer works. So in terms of the way a classical computer processes information in zeros and ones, right? So
the first talk covered very
right. So any data that goes through classical computer that is classified as 0 or 1. So the highlight here is or. So it's either 0 or 1. Just when in layman terms, in a quantum computer, that information could be 0 and 1 at the same time. So it gives you a lot of leeway to play with a lot of permutations and combinations, right, at the same time. So what a quantum computer would do, if you say that you share an image with a quantum computer and you ask if this is a cow, right? It is going to explore if there are 18 possibilities of arriving at a yes or no. It is going to explore all those 18 possibilities one by one, right? So all those permutations and combinations, they run one by one. In a quantum computer, since it has the ability to process data in zeros and ones at the same time, it can process all those possibilities in seconds. It doesn't have to go by one. All those possibilities can be explored at the same time simultaneously, and that's how you gain efficiency in terms of computing. Sorry, yeah. Your next question was around algorithms, right? So I'm not too sure because I'm really not from the technical domain, but there are some applications that are being rebuilt, retweaked, I would say. So your existing applications, algorithms in those applications are going to stay because the entire use case doesn't have to change, right? So if there is a particular use case, say in supply chain, there's a particular application. The entire application will not change. Only some algorithms in that application are going to change to basically incorporate the processing in a quantum computer. So there is no particular use case that you're going to run solely on a quantum computer. It's going to be a hybrid model. So part of the application runs on classical computer, part of the application runs on your quantum computer. So only that particular aspect of the application needs a bit of tweaking or rewriting. But otherwise, it's going to be a hybrid model.
Thank you. Ma'am, am I audible?
Yeah.
Ma'am, yeah, I have a couple of questions. First of all, you mentioned about the concerns over NISC, like the security breaches by the classical algorithms. So I wanted to ask how much vulnerable is quantum security, at least now till today? How is it vulnerable?
It's not vulnerable at the moment. So your data is secure at the moment, but there's this tendency that hackers have access to your data, right? So your credit card details, you do any transaction, you put in your credit card details. So they can hack into your system, they can get that data, but they cannot basically crack it in basically the limited time. With a quantum computer, because they already have your data, it's just that what they cannot do is process it in the required time. But with a quantum computer, they can actually process that data very, very quickly. So it is said basically in the industry that any data which is going to be relevant or meaningful or sensitive in say 15 to 20 years down the line, that needs to be protected now. So all these military conversations, government data, that's the focus, that's the priority in terms of securing data.
Okay,
even the blockchain.
Yes, ma'am. Yeah. And the next question was that there are a few types of quantum computing, like ion trap and superconducting, and then there comes a neutral atom quantum computing. So out of all these, which one is the most prospective in the industry today? If you have any opinion about that.
It is so, I think there is a lot of. So this is not just one question, everybody thinks that there is one particular architecture that's going to win the game, that's going to take the whole pie. I personally feel, I just gave you the relevance, the trade-offs of each architecture. So I feel there are a dozen of technologies now, right? It may boil down to say 6 or 7 technologies that may still remain relevant in terms of having a large, fully scalable quantum computer. But there's not going to be dependency on one particular architecture to solve those complex problems. All of that can exist at the same time because I've highlighted, I hope you were paying attention, where ion trap could be relevant, where superconducting could be relevant. So I think they have their own set of importance in these use cases, and all of this could be made available on the same network through a distributed quantum computing cluster.
So essentially, network-based quantum computing is possible for incorporating all the
right now technologies. It's hypothetical. There's a consortium in Europe who are making some advancements in this, but it's all hypothetical at this point of time. For that to happen, first you need to have scalable quantum computers. You need to overcome the problem of error rates. So there are more important challenges that you need to solve before you jump onto quantum or distributed quantum computing. So that's on the horizon, but it's not really going to happen anytime soon.
Okay, thanks a lot.
Yes, Arnav.
I think we have time for like one question.
I think there are no more questions now. If there are no hands up, so I guess
I had one question similar to the previous one. So in security domain, right? We are looking for blockchain and cryptocurrency. Would that also be vulnerable for with the advent of quantum computing put into place?
Yeah, so there's already this company, Quantum. They are already doing some implementations in terms of securing the blockchain network. So I can look that up for you and share it maybe over here. But that's just one attempt that I've seen in the last 12 to 18 months. So yes, blockchain networks will also require security.
Ma'am, is using quantum computer as user friendly as using a classical computer now? And if not, then where it will become?
No. So basically, a user will not have to get into the nitty-gritties. Like I explained, an application needs tweaking. So it will run as smoothly as classical computers. You wouldn't know the difference. It's just that the execution is going to happen very fast. So in terms of end users, you won't feel the difference. All those integrations, those adjustments, they're going to be made in the backend by technical experts. So at the end of the day, an enterprise or an end user who is basically a layman who doesn't understand quantum, that's absolutely fine. There would be APIs, available through which you can access quantum computers. So it's not going to be a challenge. You won't feel the difference.
Okay, thank you, ma'am.
Yeah, and also just to highlight, I'm available. You can reach out to me on LinkedIn in case you have any further questions. That's perfectly okay. I'm open to that. Right. So I just hand it back to you, Arnav.
Thanks a lot. That was a great talk, speaking through the professional and enterprise side, how you implement. And the thing about Omniverse was really great. None of us knew anything about Omniverse, and also that was an interesting talk, speaking about metaverses, Omniverse, and a lot of things come in the talk. I hope everybody has so many questions and they were all interested in speaking over all these questions. So in this next 1 hour, and we'll be sending you the report made by Chandrika Dutt and the report for you to read through and make a small presentation for it. And I once again thanks Chandrika Dutt for joining, and thanks for a great talk.